Another important reaction involving aromatic rings is called the nucleophilic aromatic substitution reaction. So you might recall from the the first part of this chapter that aromatic rings are generally considered nucleophiles and they can react with electrophiles in the electrophilic aromatic substitution reaction. However, under the right conditions, they can also react with nucleophiles. Before we get into that, let's discuss what would happen if we had an aromatic ring with a halogen leaving group and we try to do an SN2 reaction. You might recall from previous chapters that this reaction generally does not occur. So if we add the hydroxide ion and try to do an SN2 reaction, there should be no reaction, since in an SN2 reaction, the hydroxide ion would have to get inside of the ring to do a backside attack of this carbon to leaving group bond. And so no reaction would occur since that backside is blocked by the ring. However, if you put enough electron withdrawing groups on the ring, for example, several nitro groups, that activates that carbon to do another type of substitution reaction called nucleophilic aromatic substitution. This is a reaction that occurs through a different mechanism, and it does not involve backside attack of the carbon to halogen bond. A hydroxide ion, for example, can replace the halogen through a nucleophilic aromatic substitution, again, if we have several electron withdrawing groups on the ring. Let's look now at the mechanism for nucleophilic aromatic substitution reactions. The nucleophile, for example, the hydroxide ion, would generally attack the same carbon as the halogen, lead to breaking this double bond and putting a negative charge on the carbon that is directly attached to the nitro group. This intermediate is called the Meissenheimer intermediate or complex. This negative charge would then reform the double bond by eliminating the leaving group. Note that this reaction is very similar to the addition of a nucleophile to the beta carbon of an alpha-beta unsaturated carbonyl. For example, if we had a compound like this with an electron withdrawing group, and this could be a nitro group or a carbonyl like a ketone, generally nucleophiles will add to the beta carbon similar to their nucleophilic aromatic substitution reaction. You might recall this is the alpha carbon and this is the beta carbon. So this reaction is very similar to the conjugate addition to alpha-beta unsaturated carbonyls. The reaction is faster when we have electron withdrawing groups on the ring, especially ortho and para to the leaving group. As you can see by this intermediate, this negative charge forms at the ortho position of the leaving group. So having an electron withdrawing group like a nitro group here really stabilizes that intermediate. If we have it at the para position through another resonance form, we can also stabilize the same negative charge. As mentioned on the previous slide, having an ortho or a para substituted aromatic ring with a leaving group is beneficial for the nucleophilic aromatic substitution reaction. For example, having an ortho nitro group, after the nucleophile adds to the same carbon as the leaving group, as it usually does, it leads to the Meissenheimer complex, which has a negative charge on the carbon where that nitro group is, which is able to now stabilize that negative charge through resonance as shown here. After that negative charge reforms the double bond, by eliminating the halogen, we get a product from this reaction. The para-substituted nitro compound would do the same thing. So when the nucleophile adds to the same carbon as the leaving group, we form a Meisenheimer complex with a negative charge here. However, through resonance, we could move that negative charge to the same carbon where the nitro group is. That allows that negative charge to be stabilized. And once we reform the double bond by eliminating this leaving group, we can get to the product. When the nitro group is meta, the nitro group will be less helpful in stabilizing the Meisenheimer complex. As you can see here, when the nucleophile adds to the carbon with the leaving group, we form the Meisenheimer complex, which has a negative charge on that carbon. If the nitro group is at the meta position, it's not able to stabilize it as much. So at least at this temperature, 130 degrees Celsius, which is the same temperature we use for the ortho and the para-substituted reactants, the reaction will not occur for the meta-substituted compound. In general, the more electronegative a halogen is, the better the leaving group it is for the nucleophilic aromatic substitution reaction. This is very different from most typical substitution reactions involving halogens as leaving groups. In general, for example, for the SN2 reaction, the iodine would be a better leaving group than the fluoride. This is the exact opposite of what we see for the nucleophilic aromatic substitution reaction. This can be explained by the fact that the more electronegative the halogen is, the better the Meisenheimer complex is stabilized. As we increase the number of electron withdrawing groups around the aromatic ring, the faster the nucleophilic aromatic substitution reaction occurs. As an example, if we have a nitro group at the ortho position of this halogen, if we try to do a substitution with sodium hydroxide, we can do it at about 150 degrees Celsius and replace the chlorine with a hydroxyl group. We can lower the temperature when we add a second nitro group, one at the ortho and one at the para position, and do the same type of substitution reaction. When we add 3 nitro groups, 2 at the nitro position, ortho positions, and 1 at the para position, we can do the reaction at room temperature. Note that adding electron withdrawing groups at the meta position does help the reaction in terms of speeding it up, but it doesn't have as much of an effect as it would if we place them ortho or para to the leaving group. There are many nucleophiles as well as electron withdrawing groups that we can use in the nucleophilic aromatic substitution reaction. For example, ammonia can replace a bromine. In this particular example, notice that we have a nitro group and a nitrile that are ortho and para to the leaving group. In the second example, we're using a methoxy group as a nucleophile, and that's going to replace a fluorine. In this example, we're using an ester and a nitro group as electron withdrawing groups. We're now going to do a quick comparison between electrophilic aromatic substitution reactions and nucleophilic aromatic substitution reactions. In general, electrophilic aromatic substitution reactions are favored by electron donating groups which activate the ring because they make the ring more electron rich, which makes it into a better nucleophile. It also stabilizes the sigma complex. Electron withdrawing groups will cause the opposite. So they generally deactivate the ring. They make it less reactive. Electron withdrawing groups generally are meta-directors with the exception of halogens. Electron donating groups will be generally ortho-para directing groups. In the electrophilic aromatic substitution reactions, a hydrogen is replaced by a substituent. Nucleophilic aromatic substitutions reactions are generally favored by electron withdrawing groups. Generally, electron withdrawing groups will cause the ring to be more reactive since they stabilize the Meitner complex. Generally, electron withdrawing groups need to be at the ortho and para position to have the most effect. So in a sense, they're ortho and para directing in terms of the new substituent replacing the halogen. And the reaction overall will involve a nucleophile replacing the leaving group, typically a halogen. Here's a reaction that has been used in order to make a herbicide shown here. The reaction involves an aromatic ring with a halogen, and it's going to react with a phenol ring that also has a halogen. The reaction involved to make this herbicide is a nucleophilic substitution reaction, which involves taking the phenol and turning it into the conjugate base by adding potassium hydroxide. The phenol, or the conjugate base of the phenol, is a good nucleophile that can add to the carbon that has the fluoride, which is a very good leaving group for the nucleophilic aromatic substitution reaction. This ring is activated for the nucleophilic aromatic substitution reaction by the fact that it has a para-nitro group, as well as having this fluoride, which is a very good leaving group for this reaction. After the addition of the phenoxide ion to this carbon, we have created the Meitner complex, which will then proceed to eliminate the fluoride and reform the aromatic ring.